Okay, hello everybody. Today we're going to be introducing a new topic, which is stability. We're going to be looking at bilinear transformation. We're going to be looking also introducing Jerry array method for determining stability. However, before we get started, let's just recap what we've done in the previous module. We looked at the steady state error for different system types and for different inputs, and we created this table that we can use to easily calculate the steady state error. Now, one thing I want to get your attention to is that what happens if we have a system that is not exactly the system that we derived this table for. For instance, what happens if we have a system where we have in the forward path, we have d of z, and we want to calculate the steady state error. If it is only d of z, like the system we have here, we can just extend what the derivation that we've done when we have only g of z to include d of z. In this case, everything that we derived that will have g of z will be replaced by g of z multiplied by d of z. Again, extending it to having d of z is straightforward. Now what happens, and of course d of z or a constant, if we have a constant or d of z, the same thing applies. Now what happens if we have a system that does not have a unity feedback? Can I use the table above? I cannot. The table above is derived for a unity feedback system. Now what happens if we have a non-unity feedback? We can either derive the expression for the error and then use the final value theorem to determine the steady state value of the error. Now one thing to keep in mind is that if I have a transfer function in the feedback loop, h of z like I have here, that most likely means that the input and the output are of different nature. So if I have an input that is a voltage and I have an output that is, if I'm having a servo motor that I'm trying to control and the output is the angle theta, then I'm going to have a sensor that's going to translate theta to a voltage, and therefore I'm going to have h of z that is not unity, and therefore the output theta and the input are of different nature. So I cannot consider the steady state or talk about an error between theta and voltage. The error, if I want to calculate the error, they have to be of the same nature. Now one thing we can do, which we've done in the linear control, is I can rearrange and get an equivalent transfer function of the one that I have here by multiplying r of z by 1 over h and removing the h of z from the feedback loop and adding h of z in the forward loop. This and this, both of these have the same transfer function. However, now the error here is going to be of the same nature because I have a unity feedback. So in this case, I can calculate this error, but this error is not going to be between r and the output. It's going to be between r multiplied by 1 over h. I hope this makes sense. Now, also, I want to remind you that the steady state error only makes sense if the system is stable. There is no sense of calculating a steady state error if the system is unstable. How do we know if the system is stable? Well, this is going to be our topic for this module. We're going to be looking at stability. Okay. Now there are different definitions for stability. The one we are interested in is the bounded input, bounded output stability. And that bounded input, bounded output stability means if I have a linear time invariant system with no initial conditions, if I apply a bounded input to the system, I should get a bounded output. The input can have any value. It can reach any value, but it cannot go to infinity. It has an upper value that is m, and then the output should have an upper value that we call n. So if the input is limited by a value, the output has to be limited also by a value. So therefore, a bounded input should always give me a bounded output. Okay. Now we know that if I have a linear time invariant system described by a proper transfer function, then the system is bounded input, bounded output stable if all the roots are in the left half plane. All the poles of the system have to be in the left half plane. What does a proper mean? A proper, it means that if I have the transfer function g of s, it means the order of the numerator is equal or less than the order of the denominator. If the order of the numerator is less than the denominator, then we call that strictly proper. If the order of the numerator is less than or equal of that of the denominator, we call that a proper transfer function. Okay. Now, as we know, for the system to be stable, the poles of the system have to be in the left half plane. So this is in the S domain, the poles have to be in the left half plane. Now, if you remember, if we have poles on the j omega axis, we call that marginally stable. So if we have poles on the j omega axis, we will call that marginally stable. However, it will not be a bounded input, bounded output stable, because as an example, if I have a system 1 over S, this system has a pole at the origin, which is at the j omega axis. It's not in the left half plane. What happens if I apply to this a step input? The step input is bounded. It has a maximum value of 1. What's going to happen at the output? I'm going to get a ramp that's going to go to infinity. So therefore, it does not meet the bounded input, bounded output stability. Here I applied a bounded input, and yet I got an unbounded output. The same thing if I have, in this other example, if I have a transfer function where I have poles on the j omega axis, j1 and j negative 1. What happens if I might be able to apply some inputs where the output is bounded, but that does not make it a bounded input, bounded output stable. It has to be bounded input, the output has to be bounded for any bounded input. So if you find one input that is bounded that will make the system unbounded, then the system violates the bounded input, bounded output stability. And in this case, if I have the poles on the j omega axis, if I applied an input signal that has the same frequency as where the pole location is. So if I apply this, let me correct this, sine of t, omega is equal to 1, which is the same as the location of the pole. This is at j1, negative j1. What happens? This input is bounded. It has an upper limit. What's going to happen at the output? The output, y of t, is going to be sine t minus t multiplied by a cosine t. What's going to happen to this input? It's going to be growing all the way to infinity because of this t that multiplies the cosine t. So therefore, in both of these cases, the input is bounded, but y of t is unbounded. And that's why for the stability, we want the poles to be in the left half plane. Okay. Now, for the continuous time systems, we have different techniques for determining the bounded input output stability, bounded input and bounded output stability. We can factor the denominator and find the poles location and make sure they are in the left half plane. However, in many cases, if the order of the denominator is more than a third degree, it will be hard to find the poles locations. Now, another technique we used to determine stability is Routh-Hurwitz. We can also use Bode magnitude and phase plots, which we will be talking about in a future module. We can look at root locus to determine stability. We can also look at Nyquist plots to determine stability. Now, these methods can be used also to determine the stability of the discrete time system that is represented by g of z. That's what we want. We want to be able to apply these methods to a discrete time system. Now, method 1 and method 4 apply directly to a discrete time system. We can directly apply it to a discrete time system to determine stability. Now, method 2 and 3, the Routh, Hurwitz, and Bode, will not be able to apply directly to a discrete time system. And the reason being, for a discrete time system, in order for the system to be stable, the poles have to be inside the unit circle. For the continuous time system, they have to be in the left half plane of the S-plane. So therefore, the region that defines the stability for a discrete time system is different than that for a continuous time system. So therefore, the Routh, Hurwitz, and the Bode plots will not apply directly. Okay. So therefore, we're going to be introducing a new transform, that is the W or bilinear transform, and we're going to see how we can extend these methods that we use for continuous time systems to that of a discrete time systems. And also we're going to be introducing another method, which is the Jerry method, the Jerry stability test, that will also can be used to determine the stability of the system. Okay. So with that, we're going to be introducing our first transform, which is the W transform. Now, why do we need this W transform or bilinear transform? If we look at the continuous time systems, such as the Routh, Hurwitz, they are based on the S-plane and the stability region being, or the stability boundary being, the imaginary axis. Now, for the discrete time system, the boundary is the unit circle. So therefore, we cannot just apply Routh, Hurwitz. Routh, Hurwitz will be able to tell you whether a pole is, if I have a plane split with the j omega axis, is going to be able to tell me whether it is, my poles are on the right half plane or left half plane. But in the case of a discrete time system, what I'm looking for is to determine whether the poles are inside the unit circle or outside the unit circle. The system is stable if the poles are inside the unit circle. It is unstable if the poles are outside the unit circle. So how can I apply Routh, Hurwitz to the discrete time system? What about this? What if I come to my discrete time system and find a way to transform the locations that are within the unit circle so that they map to the left half plane, and the location of the poles that are outside the unit circle, they will map to the right half plane. So basically, I'm going to introduce a new function, a new mapping, that will map the Z plane into a W plane. This is not omega, this is W, a W plane, a W plane. So this transformation is going to take everything that is inside the unit circle, is going to map it to the left half of the W plane. Anything outside the unit circle is going to map it to the right half plane. The unit circle itself is going to be this, the imaginary axis. I hope this is clear. So basically what we are doing is that we're going to be introducing a new transform. What this transform is going to do, again, is going to take the inside of the unit circle, is going to map it to a new plane. We call it W, not omega, W. Anything that's inside the unit circle is going to be mapped to the left half plane of this W plane. Anything outside is going to map to the right half plane. The the circle itself is going to map to the imaginary axis of the W plane. This is imaginary of W, not omega. This is real of W. Now, hopefully the notation will not be very hard to understand. Just keep in mind there is a new notation which is W. Okay, so therefore in this W plane that we're introducing, if I have any location, I'm going to identify it by sigma W plus j omega W. So it's going to be complex, real part that I'm going to call sigma W, imaginary part that I'm going to call W omega W. Okay, now in order not to confuse this with the S locations, we're going to call this sigma W and omega W. Okay, what is this transformation? What is this function that can take a circle, the unit circle, and map it into the inside of a unit circle and map it into this W plane that we identified? It is the bilinear transformation. So what this bilinear transformation is going to do for us is that it's going to take the unit circle, or the inside of the unit circle, is going to map it to the left half plane of the W plane. Now why is it we're doing this? Because if I manage to map the inside of the unit circle to the left half plane like this, then I can apply Routh-Hurwitz. Now I can apply Routh-Hurwitz after we do the mapping, and to determine whether the system is stable or not. The Routh-Hurwitz can only be applied if I go to the plane and I have the imaginary axis, and it will tell me whether my poles are in the left half plane of this imaginary axis or right half plane. Now in this case, in the discrete time, I have the unit circle. All the poles have to be inside the unit circle. I'm not going to be able to apply Routh-Hurwitz to this directly. So therefore, what I'm going to do, I'm going to take the Z space. I'm going to map it using this bilinear transformation, and the mapping is such that the inside of the unit circle is going to be mapped to the left half plane. And then after I do this mapping, I can apply Routh-Hurwitz to determine whether the system is stable or not. Now this bilinear transformation, we've seen it when we studied discrete time signals, or when we studied digital signal processing, and we used it in order to design a digital control, a digital filter from a continuous time filter. Now for our purpose here, we're going to be using it for a different purpose. We're going to be using it in order to transform the Z plane to this W plane. What does this transformation look like? Z is going to equal to f of W, it's a function of W, is equal to 1 plus t over 2 multiplied by W over 1 minus t over 2 multiplied by W, where t is the sampling period. Okay, now from this I can also write W as a function of Z as equal to 2 over t, Z minus 1 over Z plus 1. Again, I can multiply across and do some simplification. I will get that W is equal to 2 over t multiplied by Z minus 1 over Z plus 1. Now what we're going to do is we're going to investigate how the poles map from the Z plane to the W plane using this bilinear transformation. Let's say that we have a pole that is located at Z equal e to j omega t. And therefore this pole is on the unit circle. And this corresponds to a pole that is j omega on the imaginary axis of the S plane. So again, now we have three planes that we're talking about. We have S plane, for continuous time systems, we have z-plane for discrete time systems, and now we have a w-plane. Now in the s-plane, if I have a pole that is at j omega, so it's on the j omega axis, where is this maps to in the z-plane? It's going to map on the z, on the unit circle. Z equal e to j omega multiplied by t. And therefore it's going to be on the unit circle. Now where is this pole that is on the unit circle map in the w plane? Let's calculate it. So we have w that is equal to over t, z minus 1 over z plus 1. My pole in the z plane is at e equal to j omega t, which is on the unit circle, because the magnitude of this, what is the magnitude of e to j omega t? The magnitude is 1. Therefore it is on the unit circle. Now what happens if I plug in that location, z equal to j omega t, in this transform? I'm going to get 2 over t e to j omega t minus 1 over e to j omega t plus 1. Now what I'm going to do, I'm going to multiply. So I'm going to multiply by e to negative j omega t over 2 over e to negative j omega t over 2. Why did I do this multiplication? Because this will enable me to simplify this expression. This factor that I multiplied here is just equal to a 1. The numerator is equal to the denominator. It's equal to 1, so I can multiply by this factor. But this will enable me to write this in terms of sine and a cosine. So if I multiply the numerator, I'm going to get e to j omega t over 2 minus e to negative j omega over 2. And the denominator, I'm going to get e to j omega t over 2 plus e to negative j omega t over 2. What is this equal to? The numerator is going to equal to 2 multiplied by j multiplied by sine omega t over 2. The denominator is going to equal to cosine omega t over 2. Of course, there's a factor of 2, there's a factor of 2. The 2 with the 2 is going to cancel. I'm going to get 2 over t multiplied by j multiplied by tan omega tangent omega t over 2. What does that mean? I took a pole that is on the unit circle, and this got mapped to 2 over t multiplied by tangent of omega t over 2, and I have this j added here. And therefore the location in the w plane, this is now in the w plane, is going to have a real value of 0, and is going to have imaginary value that is 2 over t tangent wt over 2. Okay, now I did not specify the location. I just said the location is on the unit circle. Omega t can have any value along the unit circle. So apparently any pole that is on unit circle is going to map somewhere along this axis here, this imaginary axis here. And therefore the unit circle is going to map along this line here. Now let's look at again a pole on the unit circle, as we just seen. When we map it to the w plane, it mapped to a pole along the imaginary axis at 2 over t tangent of wt over 2. Now what happens, this is on the side, what happens if t goes to 0? So let's look at what happens to this w if t goes to 0. 2 over t multiplied by tangent, if I take the limit as t go over 0, t goes to 0, I'm going to get j multiplied by 2 over t, and then I'm going to get omega t over 2 divided by 1, which is going to equal to omega. Does that make sense? Why is that the case? Because when t goes to 0, this cosine is going to become a 1. And then I'm going to have a 0 over a 0. I can take L'Hopital's rule, take the derivative. I'm going to get w and then the t the t with the t is gonna cancel. I'm gonna get the j omega. Okay. So therefore, as the sampling period approaches 0, we're gonna get omega that is equal to j2 over t tan wt over 2, and that is the location in the w plane. Okay. Now let's look some other values, some other locations in the z plane, and see where they're gonna map in the w plane. So if I look at z equal to 1, where is this gonna map to? 2 over t z minus 1 over z plus 1. If z is equal to a 1, then this is gonna equal to w equal to a 0. If z is equal to 1, 1 minus 1 is going to give me a 0. Okay, let's take what happens if z is equal to 0. Now I'm inside the unit circle. W is going to equal to 2 over t, z minus 1, z plus 1, z is equal to 0. I'm going to get negative 1 multiplied by 2 over t. I'm going to get negative 2 over t. Okay. What happens if I take z equal to j? W is going to equal 2 over t, z minus 1 over z plus 1, 2 over t, j minus 1 over j plus 1. I can multiply by negative j plus 1 over negative j plus 1. This is going to give me 2t multiplied by 2j over 2, which is going to equal to j multiplied by 2 over t. What happens if w is equal to negative j? 2 over t, z minus 1 over z plus 1. If I calculate it, is going to equal to negative j multiplied by 2 over t. So let's go and try to plot these locations and see how they got mapped. So let's look here. And let's, for the time being, ignore the S plane. So we are in the Z plane. We took these different points here. We took a point that was Z equal to 1. We took Z equal to J, Z equal to negative 1, and we took Z equal to we took Z equal to 0. So we took this point here, and we took Z equal to negative J. So if I took these points and we saw where these points map, when z is equal to 1, it got mapped to, when z is equal to 1, it got mapped to 0. So this mapped to here. When z is equal to j, it got mapped to j2 over t. So when I am at 2, which is equal to j, I got mapped, or this point got mapped to this point here. When I am at 7, I got mapped to negative j over 2. This point here got mapped to here. Now when I am at 3, which is negative 1, when z is equal to, did we take z equal to negative 1? We did not take z equal to negative 1. When z is equal to negative 1, where am I going to get mapped to? I'm going to get mapped to negative infinity. Because w is equal to 2 over t, z minus 1 over z plus 1. If z is equal to negative 1, which is 0.3 here, I'm going to get 2 over t multiplied by negative 2 over 0. So this is going to give me, it's going to go to negative infinity. So this point 3 here is going to go to negative infinity. Now if I am at the origin, which is point 4, I'm going to get, if I am at the origin, z equal to 0, I'm going to get mapped to negative 2 over t. So at the origin here, I'm going to get mapped to negative 2 over t. So this point here is going to get mapped to here. Okay. I hope this makes sense. So therefore, if I look at all these points, I notice that the unit circle got mapped into a semicircle that has a radius that goes to infinity. So therefore, this unit circle gets mapped to a semicircle that has a radius that goes to infinity. And everything that is inside the unit circle is gonna map to inside the semicircle that in the W plane. Anything that's inside is gonna map inside this semicircle in the W plane. Okay. So therefore, now that I've taken the poles location that are in the z-plane and I map them using this bilinear transformation, now the location are gonna get mapped into a plane where all the poles that are inside the unit circle are gonna be in the left half plane. All the poles that are outside the unit circle are going to be mapped to the right half plane. Now I can apply Routh-Hurwitz criteria, because Routh-Hurwitz criteria enables me to determine the locations of the poles, whether they are on the right or the left half of the j omega axis. Since I mapped everything inside the unit circle to this semicircle, and everything outside is going to map to the right half plane, everything inside is going to map to the left half plane, then I can use the Routh-Hurwitz criteria to determine the stability of this system. Okay. So let's look at an example of how we apply this bilinear transformation in order to use Routh-Hurwitz in order to determine the stability. So if I have this system here and I want to determine the stability using Routh-Hurwitz, again I cannot apply it directly. I'm gonna have to do the W transformation and then apply this to the transformed system. So first we calculate G of Z. Of course here we have S squared, so we're gonna use the table that is in the appendix in order to get G of Z. G of Z, if I plug in the value of t equal to 0.1, is going to give me this G of Z. And therefore, I can calculate the transfer function of the closed loop system, k multiplied by G over 1 plus k multiplied by G. The characteristic equation is 1 plus k multiplied by G of Z equal to 0. The denominator set equal to 0 is the characteristic equation. Okay, so now we're gonna calculate the characteristic equation. 1 plus k multiplied by G of Z equal to 0, and this will give me this characteristic equation here. Now what I want to do, again, I want to use Routh-Hurwitz to determine whether this system is stable or not. Now I cannot use it directly, so therefore I'm going to apply this W bilinear transformation. How do I apply bilinear transformation? I'm going to take Z, I'm going to replace it with 1 plus t over 2 multiplied by W over 1 minus t over 2 multiplied by W. So every Z is going to be replaced by this. This is Z. Every Z is going to be replaced by 1 plus t over 2 multiplied by W over 1 minus t over 2 multiplied by W. So after I do that, again, z is equal to this. I'm gonna rearrange the terms, and if I do that, if I square these, I'm gonna multiply by 1 minus t over 2w squared to get rid of the denominator. So here I'm gonna get 1 minus t over 2w. One of them is gonna cancel with the denominator here, and then I'm gonna get 1 minus t over 2w squared. That multiplies this constant term here. Now I can set t equal to 0.1. I'm gonna get this polynomial, that is the characteristic equation of the characteristic equation in the w plane. Okay, now this I can use Routh-Hurwitz to determine stability for it. So therefore I'm going to come to Routh-Hurwitz and generate the Routh-Hurwitz array. And if you recall, for the Routh-Hurwitz, this is the second order, so it's straightforward. W squared, this is the first, the A0 or A2 if you like, A1, A0. So this is going to be the even part, so which is going to be this term here and this term here. And then I'm going to have the odd that multiplies the odd terms in the polynomial, and this is going to be this term here. And then since this is a 0, when I calculate Routh-Hurwitz, this just comes down to here. So therefore, again, since it's a second order, it's straightforward to establish the Routh-Hurwitz. Now what the Routh-Hurwitz tells me is that all these there has to be no sign changes in order for the system to be stable. So therefore this is going to be greater than 0. This term here has to be greater than 0. This means k has to be less than 23,800. This term has to be greater than 0. So this has to be greater than 0, this has to be greater than 0, and this has to be greater than 0. This is going to result in k being less than 20.3, and then I need also 3.81k to be greater than 0, and this means k has to be greater than 0. So taking all these together, it means k has to be between 0 and 20.3. So the system is going to be stable if k is between 0 and 20.3. Okay. So what this tells me, again, is that the system poles for this value of k are going to lie in the left half plane of the w plane, which is equivalent to saying that all the poles are within the unit circle of the z plane. Okay, so this is the first method for determining the stability, which enables me to apply the Routh-Hurwitz that we are already familiar with and know how to use. We could not apply it directly. I have to take the poles from the z plane and map them using the bilinear transformation. That bilinear transformation map the unit circle into a w plane such that the unit circle, anything within the unit circle, is going to map to the left half plane of the w plane. And then after I did that mapping, I can apply Routh-Hurwitz, and that will tell me whether the poles that are mapped, if any of them are in the right half plane or whether they are all in the left half plane. And therefore, once I determine that in the w plane, that is equivalent to saying that the poles are, whether the poles are within the unit circle or outside the unit circle. Okay. Now there is another method that we can use to study stability. So the first method is to do the bilinear transformation and apply the Routh-Hurwitz. The second method is called Jerry stability test. Now this method has advantages and disadvantages. The advantage is less complicated than using the bilinear transformation. The disadvantage, unlike the Routh-Hurwitz that can tell me the number of unstable poles, the Jerry stability does not. It will only tell me whether the system is stable or not without telling me how many unstable poles I might have. Okay, so how does this Jerry test work? So let's say we have a characteristic equation, Q of z, that is given by a n z to n plus a n minus 1 all the way a0 equal to 0. We're going to assume that a n is greater than 0. If it is less than 0, we can multiply the whole polynomial by -1 to make a n greater than positive. So then what we're going to do is we're going to construct the Jerry array. How does this Jerry array work? I'm going to come here and establish this Jerry array as follows. I'm going to establish the first row, an minus 1 all the way to a0. Then I'm going to rearrange these in reverse order, an all the way to a0. This will be my first and second column. Then my first and second row. Then I'm going to create the new rows, b0 and all the way to bn minus 1. And these rows are calculated using the rows that are above them. So b0 or bk is calculated as a0 an minus k ak, and that will give me the rows, the b terms here. After I calculate this row, I can rearrange it to fill the row that is below it. And then I'm going to continue. I'm going to calculate this row, the C's, and again the C rows is going to be calculated using the rows, the two rows that are above it, which means the B's. So the C's, the C0, C1, C2, all the Cn minus 1, minus 2, we're going to use the B's to calculate them. Each row uses the two rows that are above it to calculate, and the row below it is going to be just rearrangement of the terms. Okay, so we continue doing this. Again, the elements, the first thing, the last row in the Jerry array will have 3 elements. So we'll stop when we have 3 elements. Elements that are in the even rows are the elements of the preceding row in reverse order. So if I look at the elements here, they're the same as the element here, just reverse order. Elements here in this row is the same as this one, just in reverse order. Elements here are the same as the row above it, just reverse order, and so on and so forth. Okay. So then how do we determine stability? After we created this table, the necessary and sufficient condition for the polynomial QZ to have no roots outside or on the unit circle with an greater than 0 is that Q of 1 has to be greater than 0, minus 1 to the power of n multiplied by Q of -1 has to be greater than 0. So 1, 2, and then a0, the magnitude, the absolute value of a0 has to be less than an. The absolute value of b0 has to be greater than bn minus 1. c0 has to be greater than cn minus 2. All the way to m0, absolute value has to be greater than the absolute value of m2. So after we established this table, we're going to look at the entries here, and we have to make sure they all meet these criteria. an has to be greater than a0, b0 has to be greater than bn minus 1, c0 has to be greater than cn minus 2, etc. And this is not a typo, this is less than, all the others are greater than. Okay. Now if we have just a second order system, the Jerry array will only have A0, A1, and A2. And in this case, necessarily insufficient condition for bounded input bounded output stability is that Q of 1 has to be greater than 0. Negative 1 squared is just a positive 1. Q of negative 1 has to be greater than 0. And then A0 has to be less than AN. So for a second order, straightforward to determine the stability. If we meet these conditions, this means we do not have any roots that are within the unit circle. Now for each additional order, 2 rows are added. So therefore, if we have a third order, then this is gonna require 3 rows, while a fourth order will require 5 rows. Okay. Okay. And again, there are n plus 1 constraints, so therefore, where n is the system order, so therefore for the second order, n plus 1 is gonna have 3 constraints, which are 1, 2, and 3 constraints. Okay, so let's do examples and see how we can apply this Jerry test. So going back to the example we've done before, we calculated the characteristic equation. And the characteristic equation, Q of z equal to z squared plus z multiplied by this A0. This is not A0, this is A1. Plus the last factor here, which is the A0. So applying Jerry stability, we're going to get the first condition. We need Q of 1 to be greater than 0. So therefore, we're going to substitute for z equal to 1. And if we do that, we're going to get 1 plus 1 multiplied by the factor that we have here, plus the A0, which is the factor that we have here. So if you want this to be greater than 0, then we're gonna have to have, if we add the terms together, we're gonna get k greater than 0 for this. So if we simplify this, we're gonna get 0.00952 k greater than 0. The 1 and negative 1.9 cancel out. So we're just going to have 0.00952 multiplied by k greater than 0, therefore k greater than 0. The second condition, we need negative 1 squared q of negative 1 greater than 0. So if we substitute q of negative 1, z, if we plug in z negative 1, I'm going to get 1 for z squared, and I'm going to get negative negative 1 for z, and then I'm going to get the constant. If we simplify, I'm going to get the condition that k has to be less than 23,800. Now the third condition, we want A0, the magnitude of A0 to be less than A2. And therefore I want the absolute value of 0.00468 plus 0.90505, the magnitude of the absolute value of that to be less than, this is the absolute value, not the magnitude, the absolute value to be less than 1. Now since we already know k has to be positive, so therefore I can just consider the case when 1 is positive. So therefore 0.00468k plus 0.905 has to be less than 1. And therefore, this is gonna result in k being less than 20.3. So combining all these conditions together, k has to be greater than 0, has to be less than 23,000, but it also has to be less than 20.3. So therefore, the range for k to be stable, for the system to be stable, is k between 0 and 20.3, which is the same result that we got when we used the Routh-Hurwitz criteria in the previous example. Okay, let's look at another example. So let's say that we have a discrete time system that has a characteristic equation Q of z, 1z cubed plus 2z squared plus 2z plus 0.9. This is A3, A2, A1, A0. Using Jerry test or Jerry table, since n is equal to 3, we're going to have 3 rows. So we're going to start by writing the first row, 0.9, 2, this is A1. So unfortunately they have the same number, so I hope nobody's, but that's why we have them labeled here. This is A1, this is A2, and this is A3, which is 1. Then we're going to rearrange these, 1, or reverse order, 1, 2, 2, and 0.9. Now we're going to create, or we're going to calculate the new row, which is row B, and row B is going to equal to A0, A3 is going to be B0, B1, B2, B0 is going to be A0, A3, A3, A0, and therefore we're going to take the determinant of 0.9 and 1 and A3 and A0, which is a 1 and 0.9, and therefore is going to be 0.9 multiplied by 0.9 minus 1 multiplied by 1, which is going to be negative 0.19. B1 is going to be A0 multiplied by, we're going to take the A0 multiplied by A1 minus A2 multiplied by A3, which is going to give me negative 0.2. B2 is going to be A0 and multiplied by A2 minus A1 multiplied by A3, which is going to give me negative 0.2. So therefore, after I calculated this table, I can check for the stability. I need 4 constraints, since this is third order. Q of 1 has to be greater than 0. Q of 1 is equal, going back to Q, we plug in Z equal to 1, is going to be 1 plus 2 plus 2 plus 0.9, has to be greater than 0. Okay, this is met. Negative 1 cube, Q of negative 1 has to be greater than 0. Since this is an odd order polynomial, negative 1 cube is going to be negative 1 multiplied by Q of negative 1. And that is going to give me 1 minus 2 plus 2 minus 0.9 has to be greater than 0, which is also met. Now the third condition, the absolute value of A0, which A0 is 0.9, has to be less than A3. A3 is equal to 1. This is also met. The fourth condition is that the absolute value of B0 has to be greater than the absolute value of B2. Okay, so let's see if that condition is met. Since the absolute value of B0 is equal to absolute value of negative 0.19, so in this case here, this is B0, so 0.19, and absolute value of B2 is equal to negative 0.2, which is 0.2, absolute value of negative 0.2, which is 0.2. This constraint is not satisfied. I need B0, which is 0.1, to be greater than 0.2, which is not satisfied. Therefore, this system is not bounded input, bounded output stable. Okay, so just to recap what we've done in this module, we looked at the stability of discrete time systems. We are familiar with studying the stability for continuous time systems. We used Routh-Hurwitz to determine the stability of these systems. Routh-Hurwitz applied in a space where it is divided by a j omega axis. It will tell me whether poles are in the left half plane or right half plane. I cannot apply Routh-Hurwitz directly to study the discrete time system stability, because the condition for stability for discrete time system is that all the poles have to be within the unit circle, and therefore the space that will determine the stability is different than that of continuous time system. So if I wanted to use the Routh-Hurwitz, then one thing we can do is to transform that what's inside the unit circle so that it is to the left half plane of a space that we call W. If we do that transformation, then I can apply Routh-Hurwitz to that space, to that W space. And if the Routh-Hurwitz tells me that all the poles are in the left half plane of the W plane, that translate to saying all the poles are within the unit circle in the Z plane. So that was one technique that we used to determine stability. The second technique is using this Jerry test. And this will tell me, after I establish the Jerry array, I look at the constraints, and if I meet the constraints, it will tell me whether the system is stable or unstable. Unlike the Routh-Hurwitz, if you remember, we can tell how many poles are in the right half plane by looking at how many sign changes we have in the first column. In the case of the Jerry test, it will only tell me whether the system is stable or unstable. Okay, thank you everybody.